Good morning, everyone. Today's session is today. Welcome to summer school, and today's session is about combinatorics. My name is Ayan, and I'll be your instructor. So, what is combinatorics? Combinatorics is the branch of mathematics that deals with counting, arranging, and selecting objects. So, when you have to count a certain number of objects, or I mean, mathematics, the basic principle of mathematics originated from counting itself. So, combinatorics, you can say, is one of the founding spine principles of mathematics. It focuses on how many ways something can happen under specific conditions. So, that is again used in probability and other places. So, suppose you want to find how many ways something can happen, and you are given certain restraints and constraints, and then you can use combinatorics to find that. It basically makes counting easier. Counting small number of objects is easy on hand, but counting when you have a large set of objects and a large set of things that you have to count, which is generally what we need it for. We can count small things on hand itself. So that you require combinatorics. That makes it much easier to count. So why is it important? Combinatorics is used in probability theory. It's used in computer science, statistics, operations research, and everyday problems. Probability theory, because in probability theory we use to find the probability of anything happening. Basically, we have a lot of elements in the sample space. So to select out of those many elements, we can't just select by using our basic arithmetic. So you need to use combinatorics to do that. And computer science, algorithms, and cryptography, the same thing as passwords. So statistics and operations research. So statistics is basically if you want to see, again, that is also coming under probability theory a little bit. If you want to see suppose you want to know uh, what is the statistics of it raining tomorrow. So basically what they do is you need to find the number of days it has rained before and then divide by total number of days. So that is the number of days it has rained before on the same day. So all that is required to combinatorics to count. So you can't count such big numbers by using simple arithmetic. So everyday problems including passwords and lottery numbers. So passwords are basically the reason why passwords are difficult to break is because there is a very less chance of someone opening that password, because there is a very high number of tries you have to put in to get that particular password. How do you calculate the number of tries? Again, combinatorics. Okay, so topics we cover today is basic counting principles, factorials, permutations, combinations, inclusion, exclusion principle, counting as repetition, binomial theorem, and Catalan numbers. So, the multiplication principle. What is the multiplication principle? The concept of the multiplication principle is to find the number of ways to perform a sequence of independent tasks. I'll give you an example, and if there are n1 ways to do task A and n2 ways of doing task B, then there are n1 and n2 ways to do both. What that means is that suppose you have, say, let's look at the example. Suppose you have to choose an outfit to wear tonight and have 3 shirt options, 2 pant options, and 4 shoe options to choose from. So I have 3 shirt options. I have 3 shirt options, 2 pant options, and 4 shoe options to choose from. Suppose these 3 shirts are S1, S2, and S3. Now, if I want to choose an outfit, I require to wear a shirt, pant, and a shoe, right? So for every time I wear shirt 1, I can choose either pant 1 or pant 2. And for each of these, I can choose any of those 4 shoes. So S1, pant 1, shoe 1 will be one outfit. S1, pant 2, shoe 1 will be another outfit. S1, pant 1, shoe 2 will be another outfit, and so on. You'll get 4 outfits with just S1 and pant 1. So shirt 2 and pant 1 will get again 4 outfits. In that way, so for the first place, for the shirt, we'll have 3 options. For the pant, we'll have 2 options. And for the shoe, we'll have 4 options. So for each shirt, I have 2 pants, and for each pair of shirt and pant, I have 4 shoes. So that will give me 24 outfits. This is the application of multiplication principle. So that's why you get 24 outfits. Now, another example is creating a 3-digit pin So again, that is again used in password. So why is it? How many ways can I create a three-digit pin? So there are three digits, and in each digit, in each place, I can place 10 numbers. So I can place 0 to 9. I can place any of these digits in each of these places. So in the first place, I can place either 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 digits here. So the first place I can place 10 digits. For each digit placed in the first place, I can place 10 more digits in the second place and 10 and so on in the third place. That would give me 10 power 3. That is 1000 pins. Next. So that is 1000. Now, addition principle. The concept of this is how to find the number of ways to perform one out of several mutually exclusive tasks. So, if you have n1 ways of performing task A and n2 ways to perform task B, and you cannot do both at the same time, then there are n1 plus n2 ways to do either A or B. See, let's look at the example. Choosing a course out of 5 math courses or 4 science courses. So, I have 5 math courses and 4 science courses to choose. I can choose any of these. Not like I have to choose a math course and a science course only. It's not. They are not dependent on each other. They are independent. So they'll be treated as 9 different courses because 5 plus 4 is 9. So I'll have 5 plus 4 equals 9 choices. Right. One second, my thing is behind. Yeah. Yeah. So another example is rolling a die and getting an odd number or a number greater than 3. So a die has 6 sides. Uh, an odd number is 3, 5, and 1. And number greater than 3 is 4, 5, and 6. So the chance of getting an odd number or a number greater than 3, out of this, there are 6 chances. There are 3 chances. So any of those. So totally 6. Each of them has 3 and totally 6 outcomes. Now, this is a question. So Mr. and Mrs. Zeta want to name their baby Zeta so that its monogram will always be in alphabetical order with no letters repeated. How many such monograms are possible? So basically, what a monogram is see, suppose A, B, C is a monogram because it is in alphabetical order, and B, A, C is not a monogram. So basically, what they're doing is Mr. and Mrs. Zeta are naming their baby Zeta. So there are 3 names for the because it has first, second, and third, middle, and last initials, right? So there are 3 letters in the baby's name, and the last initial will obviously be Zeta according to the question. So now you have to find the number of monograms. So the first and second and last are in alphabetical order. I'll give you 5 minutes to solve this, and I'll solve it after that. You can put your answers in the chat. Okay. Okay, so your answer will be, let's solve this. Uh, the last letter is fixed as Z, no? So monogram means it's alphabetical order, so you cannot repeat letters obviously. So they'll be first. So first letter will fix it as A, because right now we'll not use any 25C. We'll not use C and P. We'll just do it normally because that's not been covered. So the first letter is fixed as A. If the first letter is fixed as A, the second letter can be from B to Y, any letter, right? So that we'll have 24 letters. 24 choices for A and Z as first and last letters. For B and Z, we'll have 23 choices, and so on, right? And the last one will be one choice, that is X, Y, and Z. This is the last possible choice. So total number of choices will be 24 plus 23 plus and so on plus 1. So the sum of n natural numbers from 1 to 24. That is 24 into 25 by 2. That is 300. So 300 is your answer. If you have any doubts, you can ask in the chat. Your answer is 300. If you have any doubts, you can ask in the chat. I will let 2 minutes pass for doubts as well. 1 second. My screen is hard. Yeah. Okay, you want me to explain this again? So the question was, Mr. and Mrs. Zeta want to name their baby Zeta. So that its first monogram, will always be in alphabetical order, right? That means the first, second, and last initials will be in alphabetical order. So this is Z because the last letter of the name is Zeta, so it's Z. And now we'll take for the first case the first letter to be A, right? Because we'll start doing it systematically. So A, the second letter can be anything from B to Y because then it will be in alphabetical order, right? The same way, if second letter is B, it can be anything from C to Y. That then also will be alphabetical order. There are 24 choices here, 23 here, and so on. And the last case will be X, Y, Z, that is one choice. So that the total number will be 24 into 25 by 2, which is 300. Why is that? Because it is a sum of first and natural numbers is n into n plus 1 divided by 2, right? Next. Factorials. So the definition of a factorial is the product of all positive integers less than or equal to n. The formula is n factorial is n into n minus 1 into n minus 2 and so on into 3 into 2 into 1. So this is an example of that. Basically, you must be knowing factorials, but still. So the connection to counting is it represents the way of number of ways to arrange n distinct objects. So basically, if I have n objects and I want to arrange these n objects, the number of ways is n factorial. Why is it n factorial? Because say, I have n spaces now to arrange them in. Because I'm going to arrange all these objects. So I'll just create spaces for them to be arranged in. So the first space, I can arrange any of these n objects. So I can arrange them in n ways. The first place can be filled in n ways. Each object, I'm considering a different way of filling the first place. The second place will be filled in n minus 1 ways. Why? because the first place is already occupied by one object. So we have only n minus 1 objects left to fill the second place. And this recursion continues. Therefore, for every n object, and every of those n ways of filling the first place, there will be n minus 1 ways to fill the second place, n minus 2 ways to fill the third place, and so on, till we finally reach 1. And this is equal to n factorial. Actually, this is done. Next. Permutations. Okay, so this is the main thing. This is where it starts. So, definition of permutation is an arrangement of objects in a specific order. So, remember this, order matters, right? Order matters. This is very important. Uh, you'll understand later on why. So, formula of permutations is that permutation of n objects taken r at a time is npr. This is basically npr is equal to n factorial by n minus r factorial, right? Now, permutation of all n objects. And why is it n factorial by n minus r factorial? So, the same way, the same case, okay, but I'm taking only r at a time. I'm taking only r at a time. So basically, what I'm doing is I'm taking only the first r places. So it will be n and so on till n minus r only. So that will be n factorial. N factorial. It will be only till. So basically, that will be n factorial by n minus r factorial. Why? This will be n minus r minus 1, by the way. Okay, so why is that? Because for one object, it is n minus 0. For 2, it's n minus 1. So for n, it will be n minus r minus 1. So the last place here will be n minus r minus 1. So that will be n into n minus 1 into and so on till n minus r minus 1. Right? And this we can write as n factorial by n minus r factorial, because n factorial can be written as n into n minus 1 into so on into n minus r minus 1, and then again it will go on, right? So that we can just write it as n minus r factorial, right? So n factorial, when if you divide by n minus r factorial, we get this, which is the same thing. That is why it is n factorial by n minus r factorial. Formula. Permutation of all n objects is p of npn basically. So npn is n factorial by n minus n factorial. And by the way, 0 factorial is 1. So it's n factorial itself. Next. Arranging the letters of the word apple. Taken 3 at a time. So basically what I'm doing is I'm considering these two p's are different. Okay, because we are still in permutation. Let's not confuse ourselves. Considering those two p's are different, the number of ways of arranging is 60. Next. Selecting a president, vice president, and secretary from 10 people. Okay, so you just note this problem and keep. So selecting a president, a vice president, and a secretary from a group of 10 people, right? That I need to select 3 people, 3 distinct people. Order here matters. You will understand. I can do that in 10p 3 ways. Okay. So that is because selecting R 10 3 out of 10 objects, I'm selecting 3 objects. Taken 3 at a time. So that will be a permutation of 10p3. That is 10 factorial by 10 minus 3 factorial, which is 10 factorial by 7 factorial. That is 10 into 9 into 8 into 7 factorial divided by 7 factorial. That is 720. Right? You can see that. Next. So, again, a few questions for you. How many different ways can the letters of the word mathematics be arranged such that the vowels always come together? I'll give you 2 minutes for this, or maybe 3 minutes. Okay. I'll solve this at 9:30. You can put your answers in the chat. Okay, so see if you all have answered. Okay, we'll solve this now. So, mathematics, right? What is the question? The question is, how many different ways can the letters of the word mathematics be arranged such that the vowels always come together? So the vowels in mathematics are A, E, A, and I. So that is A, E, A, and I. These should always come together. And the remaining are M, T, H, M, T, H, M, T, C, S, right? 1, 2, 3, 4, 5, 6, 7. Yeah. So there are 7. If these vowels always come together, what I do is, to simplify our process, I will take 8 spaces, 7 for the consonants and 1 for the group of vowels. Right? So in these 8 places, I can permute these 8 groups in 8 factorial ways. But I have M, T, and T repeating. So M will be repeated twice and T will be repeated twice. Right? And you'll have 4 of these. Okay, so this is the first step. Okay, that is step 1. 8 factorial by 2 factorial into 2 factorial. Now, even in this group of vowels, we need to permute them again together. That is, there is no restriction that they cannot be permuted together. So every permutation of these vowels is considered different. So that will be into 4 factorial by 2 factorial ways. Why 2 factorial ways again? Because A is repeated twice. So if you simplify this, you should get your answer. Whoever wrote this is the right answer. So let's simplify it for the sake of 8765 into 4, 3, 2, 1, right? This is basically by 2 again. So 8 factorial by 2 is what we want. No, my bad. 8 factorial into 4 factorial divided by 2 factorial into 2 factorial, right? So that will be 8 into 7 into 6 into 2. 4 factorial by 4 is 6, right? So 8 sevens are 56 into 30. This is 12. 12 into 12 is 144. That will be 56 into 3. 18, 16, 168. 24, 26, 662. which is basically 8 factorial into 4 factorial by 2 factorial into 2 factorial into 2 factorial again. So this is the answer. That will take a lot of time to do. So whoever got that is the right answer. Next. The next question is, how many three-digit even numbers can be made using the digits 1, 2, 5, 6, 7, 8, and 9 if no digit is repeated? It should be easy. I'll give you 1 minute for this, and we'll see in 1 minute. So I shall check. Do you guys want 1 more minute, or should I solve the question? This one, yeah. No digit is repeated. Yes. Nice. Patil Raj, Brother Madhav. Nice, nice. No. Should I? I'll solve this question. So the digits what we have are 1, 2, 5, 6, 7, 8, and 9. So 1, 2, 5, 6, 7, 8, and 9. Three-digit even numbers, right? So the last digit is an 8, a 2, or a 6, right? So the last digit will be an even number for it to be an even number. Suppose we fix the last digit as 2, then we have the first place can be, we'll have 1, 2, 3, 4, 5, 6 ways to fill the first place, right? We'll have 6 ways to fill the first place and 5 ways to fill the second place. Why? Because we've only chosen one digit and the next digit will come in the second place. And we have only 3 ways to fill the last place. Why? Because there are 3 digits. There are 3 even numbers, 2, 6, and 8. So for each of them, it's the same thing. So there is 3 ways. 6 into 5 into 3, that is 15 into 6, that is 90. So whoever got 90, that's the right answer. Yeah. This is not working. 1 second. Okay. Let's go back. So the answer for this is 90. And the answer for this was 8 factorial into 4 factorial by 2 factorial into 2 factorial into 2 factorial, right? How many numbers are there between 100 and 1000 such that at least one of the digits is 5? This should be easy. I'll give you 2 more minutes for that. I shall solve at 9:39. Okay, so let's solve this. Let's look at the answers first. Really nice. Let's solve this as well. So 100 and 1000, right? So what they're asking is the number of three-digit numbers with at least one five, right? So three-digit number. Suppose the last place is a five, and to make our calculation simpler, we will not fix five in the first and second places. We will add them up later on. We'll add the cases up using the addition principle. So the first time, the last place is five. The first place can have any digit except 0 and 5. Because if 0 is there in the first place, it is not a three-digit number anymore. So it can have 8 digits totally. The second place can have any digit except 5, and that will give us 9 digits. So 72 ways in which the last digit is 5. Second digit is 5, same thing repeats, 72 ways. Now, if the first digit is 5, then the second and third places can have 9 digits each because they can have anything except 5. Because a 0 in the second place is still a 3-digit number, makes a 3-digit number yet. So 81 ways because 9 into 9 is 81. Now the last place, if there are two fives, suppose the first and second places are 5, we'll have 9 ways. No, yeah, we'll have 9 ways because the last place will not be 5. Now the first and second and last is 5, again 9 more ways. And second and last is 5, we'll have 8 ways, right? And now suppose, and we have one more case that is with all are 5s. That is one way. Now we'll add these up. Your answer is the sum of these. That is 72 plus 72. And now plus 81 plus 9, 9 and 9, 27. Right? That's 144 plus 81 plus 27. That is 144, 81 is 5, this is 2, this is 225. 252 is your answer. Any doubts you can ask. If you got a different answer or this looks to be wrong, you can always ask. Next. Okay. So this is 252. Right? The next one. 11 animals in a circus are to be placed in 11 cages. If 4 of the cages are too small for 6 of the animals, then find the number of ways of caging all the animals. I'll give you 5 minutes for this as well. This is a good question. You can try solving it. Okay. So let's see if you all have got the answer. Nice. Nice, nice, nice. Crazy. Let's do it ourselves now. Let's solve this. So we have 11 animals, and they're telling we have 4 cages which are too small, right? For the animals. So we'll divide the cages into two types. 11 animals and 11 cages. We have 11 animals and 11 cages, right? So we'll divide the cages into two types. 4 are small cages, and obviously 7 will be bigger cages. And because there are 4 small cages, they converse. So 4 big animals and 7 will be small animals, right? So in these 4 small cages, only these 7 small animals can be fit in. These 4 big animals cannot go into these 4 small cages. So this I can do that in 7p 4 ways, right? Because I have to permute these 7 animals out of these 7 animals into these 4 cages. Now remaining will have 11. We'll have 7 cages left. In those 7 cages, we can fit any animal, either a small or a big animal, because big cages can fit even small animals, obviously. So then I can fit them in 7 factorial ways because I'll have 7 animals and 7 cages. So the answer is 7p4 into 7 factorial. That will give us 7 factorial by 4 factorial into 7 factorial. 4 factorial is 24, 5 factorial is 120, 6 factorial is 720 into 7. 720 into 7 into 7 into 6 into 5. So 720 into 30 into 49 is our answer. Let's see what have you guys given. 6 animals are too big. No, 6 animals are too big. Yes, my bad. Right. Very good. Thanks for noticing. Right. Yes. So 4 are too small for 6 of the animals. So we can't fit. So there are 6 big animals and there are 5 small animals, 4 small cages, and 7 big cages. Right. Right. Thank you. Nice one. Rashid. Right. Yes. So in these big cages, in these small cages, only these 5 small animals can be fit. So that is 5p 4 ways, right? And we'll have remaining 7 factorial. So 7 factorial into 5 factorial. Whoever answered this is the right answer. Correct. My bad. Amal, B, and who else? That should be 15120. So I guess, yeah, Rishit is also right. Nice. Well done. So it's 7. Bro, why is this? One second. Yeah. So this is 7 factorial into 5 factorial. Anyone who got this, that is the right answer. Next. Combinations. A selection of objects where the order does not matter. Is combination. Right? So always remember the order does not matter in a combination. This is a key point. Whereas in a permutation, the order matters. Order of selection. Combinations of n objects take an r at a time. So that is NCR basically. This is NCR, that is n factorial by n minus r factorial into r factorial. Next. Relationship to permutation is NCR is equal to NPR by r factorial. It is quite evident. This is NPR and this is r factorial. So yeah. Choosing a committee of 3 people from 5 people. See, basically there was another question. You remember that was choosing a president, vice president, and secretary from 10 people. Here the order mattered because suppose if I choose person 1, person 2, person 3 to be a president, vice president, and secretary, person 2 becomes a secretary, that will be a different order, basically. So that is where the order matters. So that came under the class of a permutation. This is classified as a combination because person 1, person 2, person 3 We just selected a combination of these three people. So basically, they can be chosen in 5C3 ways because we're choosing three people out of five people. So that is 5C3. That will be 5 factorial by 2 factorial into 3 factorial. That will be 5 into 4 by 2. That is 10 ways. Right? So we saw 10 ways. So basically, the main difference between a combination and a permutation in simple words is that, see, if A, B, C is a set of letters, now I have to choose a combination of three letters from this. That is only one combination, that is ABC. If I have to if I choose a permutation of these, then ABC, BAC is also ACB is a permutation, BAC is also a permutation, BCA is also a permutation, and CAB, CBA. These are all permutations, right? Of this particular of ABC. Here the order matters. So first time when A is first, B is second, C is third is one order. A first, C second is another order. But if I'm telling you to choose a combination, I just have to choose these three letters. That's all. It does not matter what order they are in inside. That is a combination of these three. Why it matters, you'll know. So selecting a 5 cards from a standard 52 card deck is 52C5, 52 factorial by 52 minus 5 into 5 factorial. That is this. Properties of combinations. NCR is equal to NCN minus R. NCR is equal to NCN minus R. So we take NCN minus R, that will be n factorial by n minus R factorial into into n minus R factorial. That will be n factorial divided by n minus n is 0 plus r factorial into n minus R factorial. This is basically NCR. So we prove this. Now NC0 is 1. Why is NC0 1? Because NC0 is equal to n factorial by n minus n factorial into 0 factorial into n factorial. So that will be n factorial by n factorial, which is 1. Next, NCN is also 1 because we can use the same property to prove that. NCR is equal to n minus 1 CR minus 1 plus n minus 1 CR. Pascal's triangle is basically because if you keep adding, it keeps going on. So that is why you can form a Pascal triangle with that as well. So NCR is equal to n minus 1 CR minus 1 plus n minus 1 CR. So to prove this, we'll take the RHS first. So the RHS is n minus 1 CR minus 1 plus n minus 1 CR. That will be n minus 1 factorial by n minus R factorial into R minus 1 factorial plus n minus 1 factorial into n minus R minus 1 factorial into R factorial. So we'll take n minus 1 factorial common. We'll take n minus R minus 1 factorial common. We'll take R minus 1 factorial common. And then inside we'll have 1 by n minus R plus 1 by R. That will give us n minus 1 factorial divided by n minus R minus 1 factorial into R minus 1 factorial. R plus n minus R is n divided by R into n minus R. Right? So n into n minus 1 factorial is n factorial divided by n minus R minus 1 factorial into n minus R is n minus R factorial into R factorial. So that is NCR. Now, again, you can solve the first question and then we'll do the second and then the third. So you can put your answer in the chat. I'll give you 5 minutes for each question. The first question I'll give you 6 minutes, okay? So at 10 o'clock I'll solve the first one. You can solve all three also, it's your wish. You can put them in the chat. I'll do all of them.
I am.
Yeah.
We'll take attendance now.
Okay. Okay.
Okay, guys. Who are there? Put your names in the chat for the first round of attendance.
I'll give you another extra minute. No, no worries. You can solve the first question if the attendance took your time. Okay. Have you all gotten the answer? No worries. I'll wait for some more time. Just the first question. You don't need to do all of them together. Just the first. Any one of those. You can just tell me question one, question two, or question three, and your answer in the chat. Just put it if you got the answer. If you didn't, it's no problem. I'll solve it anyways. Yeah. So I think right two. Third one is not 2952. You can check again. Rishit. Third one is not 2952. Okay, the first one we'll do first. So a polygon of 10 sides, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's not, it does not look nice, but it's a 10-sided polygon. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sides. Yeah. So we'll name the vertices first. So B, C, D, E, F, G, H, I, and J, right? So the first case, we'll have of these, this, and this, and this, and it'll basically be this, but that is, it does not look that neat, but okay, we'll just make it look better, right? 1, 2, 3, 4, 5, 6, 7. Nada. So 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It does not look good even now. I'm sorry, but C, D, E, F, G, H, I, and J, right? BJ is one parallel diagonal. CI is one more. HD is one more. GE is one more, right? So this is case one. There are two cases. Keep in mind, this will be case one. Here the parallel diagonals are BJ, CI, DH, and EG. CI, DH, and EG. There are four pairs of parallel diagonals. Now, for each of this, we can take five sets because we're taking two points each way, no? So 10 points. So we'll take five sets of points. We'll get five sets of points. And out of these two, we have to select a pair of parallel diagonals. A pair of parallel diagonals meaning any two of these two will be a pair of parallel diagonals. So we have four diagonals, out of which we have to select two pairs of parallel diagonals. One pair is having two, so two out of them, and we can do that in five sets, five ways, because there are five. There'll be five such sets, right? Because if I shift this point to A, if I shift this point to B, like if I shift this point to A, it'll be this, and if I shift this point to B, it'll be this, and so on. So each of those sets, there'll be five such sets. Because again, when I shift the point to J in the ending, or it'll come back to JB. JB and BJ are the same line. So we'll have to, there'll be 10 points and 5 will be repeated. So 10 minus 5 is 5. Or you can do as 10 points, uh, each diagonal set of 2 points, so 5 sets. Anyways, so 4C2 into 5. That is case 1. Number of parallel diagonals in case 1. Right? Case 2. Now, case 2, again, case 2 will have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So we'll name the vertices again: A, B, C, D, E, F, G, H, I, and J. In case one, what we did was we took B and J, right? Now we'll take all the diagonals parallel to AB. We'll take CJ. We'll take CJ. We'll take DI and EH. Right? DI and EH. So there'll be three pairs, and again there'll be five such sets again, because again 2 points, and we can keep shifting them. When it comes back to the reverse point, it'll be the same thing. So five sets. So five sets, and out of these three, we have to select any two because we need a pair of parallel diagonals. So 5 into 3C2. That'll be in case 2. So your net answer is 5 into 4C2 plus 5 into 3C2. That would be your net answer. So that is 5 into 4 into 3 by 2. It's 30 into 30 plus 15, 45. Your answer is 45. The first answer is 45. Bro, this thing. So the first answer is 45. If you got 45, that's very good. If not, no problem. We're still learning. It's fine. So the first answer is 45. The second answer. In a plane, there are five straight lines and that pass through a given point. Six others which all pass through another given point, and seven others which all pass through a third given point. Suppose no three lines intersected at any point and no two are parallel. Find the number of triangles formed by the intersection of a straight line. Straight lines. Okay. Let's let's see. You can try solving it again. You can try solving this as well. Third one is 1296. Yes, right. Correct. Second one. You can try solving this second one. Yeah. I'll give you 5 minutes for this as well. Third one, I'll just do it fast. Don't worry. I'll solve this at 10:10. You can put your answer in the chat for the second one as well. Second one, people who have not solved third one, you can solve third one and try putting an answer. It's okay if you're wrong. The answer for the third one is 1296, like people have already said. Yeah. We'll solve the third one, don't worry. Anyways. Second one is not 2 and 10. No. Okay. I saw the second one, I guess. It's 10:10. Yeah. So, second one. Right. The question is, there are five straight lines that pass through a given point. We'll name the first point, just for convenience, we'll name the first point as point A, the second point as point B, the third point as point C. So there are five straight lines that pass through point A, right? 1, 2, 3, 4, and 5. This is point A. and there are 5 straight lines passing through this point. Point B, there are 6 straight lines, correct? Yeah, 6. 6 straight lines passing through point B. And 7 pass through point C. Note that to form a triangle, we need 3 lines, right? We have how many lines? We have 5, 6 plus 7. We have 18 lines. Out of those 18, we need to select any 3 lines, right? But in this selection, we included some wrong triangles, like which do not actually form a triangle. So you notice that lines passing through 3. Okay, so these 3 points are not collinear. Okay, obviously not collinear. Then the question does not make, because not mentioned. So no 3 lines intersect at any point, and no 2 are parallel. So that's, if they are collinear, then these 3 lines, then these 2 are parallel lines. Lines passing through A and B will become parallel lines and also intersect at infinite points. So just for the sake of writing, I wrote these 3 points like this. They are not actually collinear. These 3 points are not. So just let us make it again. So this is A, this is B, and this is C, point C. A has 5 lines passing through that, 5 straight lines. B has 6 straight lines, and C has 7 straight lines. Okay, and no two lines intersect at any point. Obviously, no 3 lines intersect at any given point, meaning these 5 straight lines obviously intersect at a given point. No 3 lines, meaning another 2 lines are not intersecting at the same given point. With these, except these 5 straight lines, these lines do not intersect at this point. These 6 lines don't pass through these 2 points at all. That is basically the question. Okay, so 18C3 ways of selecting 3 lines out of these 18 lines, minus 3 lines passing through the same point will never form a triangle. Okay, it's obvious. So all selections in which all 3 lines pass through point A, plus selections of which in which all 3 lines pass through point B, plus selections in which all 3 lines pass through point C. That is 18C3 minus 5C3 plus 6C3 plus 7C3. Basically, 18 into 17 into 16 divided by 6 minus 5 into 4 divided by 2 plus 6 into 5 into 4 divided by 6 plus 7 into 6 into 5 divided by 6, right? Yes. So this is 3. 17 3s are 51. Yeah. 51 into 16. Yes. 51 into 16 minus 10 plus 20 plus 35, right? So 51 into 16, 6, 30, 1, 5, 816, 816 minus 10 plus 20 is 30, 65. That is 751. So our answer for the second question is 751. Any doubts? Many of you got the wrong answer. So if you have any doubts, you can ask in the chat. The chat is open. Yeah, 751. Right. Mridul Madhav and Patil Raj Sanjay. Very good. Right answer. Next. Counting with repetition. So selecting objects for the same objects can be chosen multiple times. So combinations with repetition, the formula for that is n plus r minus 1 CR, where n is the number of objects to choose from and r is the number of objects being chosen. Choosing 3 scoops of ice cream from 4 flavors. 4 plus 3 minus 1, C3. 6 C3, that is 20. If you have any doubt in all this, you can just ask me. It's better applied intuitively than remembering this formula, according to me, but okay. The inclusion exclusion principle. It is a powerful technique for counting the number of elements in the union of multiple sets, especially when there are overlaps. The core idea of the inclusion exclusion principle being that to count the number of elements in the union of sets, we sum the sizes of the individual sets, then subtract the sizes of the intersection of pairs, add back sizes of intersection of triples, and continue the recursion for as long as it requires. I'll explain this in a very simple way. See, 2 sets. The best way to visualize sets is by a Venn diagram. and because it's two sets, it's a Venn diagram. So not to visualize more than three sets are basically difficult to be visualized in a Venn diagram. So two sets, set A and set B, suppose. Now set A suppose has m elements, set B has n elements, and A intersection B has p elements. Okay. Now this n of A union B is m is equal m plus n, which is not. It's not m plus n. Why? Because we're counting this intersection twice in counting that. Because first time we count m, we're counting this p. Second time again we're counting this p. So we have to subtract p, and that will be equal to it. Or simply, this portion will have m minus p elements, and this portion will have n minus p elements. So that will be m minus p plus n minus p, which is m plus n minus p. It's the same way it goes on for third, triplets, for three sets, four sets, five sets, and so on. So you're including them once, and you're excluding them again because you included them two times, not one time. I'm including p two times. When I'm counting A also I'm including, when I'm counting B also I'm including p. So I'm removing that extra p which I got. That is why we're excluding that. That is inclusion exclusion principle. That is basically what it means. The pigeonhole principle. If you have n items, pigeons, the name of the principle derives the name from pigeonhole, so we consider them, we use pigeons and holes here, pigeonholes here. So if you have n items which are to be placed into m containers, and n is greater than m, then at least one of the containers must contain more than one item. Okay, it is very simple to explain. So suppose I have five sticks. I have five sticks, and I have four boxes. Okay. Now I have to place these five sticks into these four boxes. Suppose I begin placing them in the most ideal way, and I want to prove the converse of the opposite of the pigeonhole principle, which you cannot prove. We'll tell you that. So the first, I put one stick here, one stick here, one stick here, and one stick here. But I have one stick extra left. This is extra stick because there are five sticks, no? So m greater than m. So this extra stick has to go in one of these four boxes. So that is how we prove pigeonhole principle. That is basically the pigeonhole principle. The pigeonhole principle can be generalized as follows. If n items are to be placed into m containers, then at least one container must contain at least ceil of n by m. That is, the ceiling function of a certain rational number is the smallest integer that is greater than or equal to this rational number. So the ceiling function of 0.2 or 0.3 or anything 0 point something is equal to 1, because 1 is the smallest integer greater than or equal to this particular, the value inside the ceil function. So that is the smallest integer greater than or equal to x. Application. The pigeonhole principle is often used to prove existence theorems. Example, proving that in a group of 13 people, at least two must share the same birth month. Because we have 12 months and we have 13 people, right? So these 13 people, if suppose in the best case, each of them have different months, only 12 of them can have distinct months. Another one of them has to have the same birth month as the other 12, the remaining 12, because there are only 12 months. You cannot have 13 months. Next, the binomial theorem. The binomial theorem provides a formula for expanding the expressions like x plus y whole power n. So this is binomial theorem is basically this: x plus y whole power n is equal to sigma r is equal to 0 to n ncr x bar n minus r y bar r. That is the binomial theorem. This is again okay. Okay. Catalan numbers. So if you do not know Catalan numbers, it's a good time to learn it. A sequence of natural numbers that occur in various counting problems, often involving recursively defined objects denoted by Cn for n is equal to one second. For n is equal to 0, 1, 2, and so on. The explicit formula of Catalan number is Cn is equal to Cn is equal to 1 by n plus 1, 2n Cn. This is the formula of a Catalan number. 1 by n plus 1 to n zero. This is a recursive formula for Catalan number that is, well, it is basically like you're trying to generate a function, generate a Catalan number by using previous Catalan numbers. That is, the first few Catalan numbers are C0 is 1, C1 is 1, C2 is 2, C3 is 3, C4 is 4, and C5 is 42, and so on. Okay. So the next few common applications of Catalan numbers. It's not Dikpath, it's parenthesization. Let's change it right here, right now itself. It is not Dikpath, it is parenthesization. So yeah, a famous ancient question in this context is how many distinct arrangements of n pairs of left-right parentheses are there, all of which close. That means basically how many valid pairs of left-right parentheses can you have? How many arrangements can you have of a given pair of parentheses? Suppose I have one pair, I have only one valid arrangement. This is not a valid arrangement, right? This is not a valid parenthesis at all. So the same way they're running for n pairs. That will be the nth Catalan number. Okay. So C1 is 1. So you can see only one pair. C2, these are the two pairs. C3, this three pair. C2. So C3 is 5. So 1, 2, 3, 4, and 5. This came off on the left side by mistake. And that's it. So this is C2. My bad. Where did it go? Yeah. This is C2. These two are C2. And these 5 are C3. Right? The number of ways to parenthesize an expression with n binary operations or n plus 1 factors is given by the nth Catalan number. Remember this. You will be given a question later on based on this itself. So, dig paths. A dig path of length 2n is a path on a grid from 0 to 0 to n comma n using steps, only steps 0 comma 1 up and 1 comma 0 right. Such that the path never goes above the main diagonal y is equal to x. So this would be a example of a dig path. Okay. And this is not an example of a dig path. And neither is this. Because this is the x is equal to y diagonal. It cannot go above that. Because to go above the x is equal to y diagonal, I need a move in this direction. But we are restricting movements only to this and this direction. That is, this is we are considering up and this we are considering down. Or right. Here we are considering right. This is considered right. Okay. How many dig paths are there? For n is equal to 2, there are paths from 0, 0 to 2, 2 are 1. Right, up, and right up. Right. So there are two paths, that is C2 is equal to 2. Do you want to see the proof of Catalan numbers by using dig paths? I can show it to you because we're running short of time. If you want to see, I can show it to you using combinatorics. You can put it in the chat if you want to see. Nice. I'll show it to you. Yes. So now suppose we have certain dig paths. Let's suppose we take one thing like this and like this and like this and like this. Okay. Yeah. So this is 1 and this is 2n, suppose. Okay, this is 2n. So to prove the number of dig paths, now what we know in a dig path is the total length of the path is 0 because the number of ups has to be equal to the number of downs for it to come back in the same position in the ending, right? Yes or no? You can type, okay, yes or no. So the number of ups has to be equal to the number of downs. So we'll write that first. The number of ups, this is not a dig path, by the way. This is not a dig path. We'll come to that later. A dig path is always above the x-axis. This is going below the x-axis. The number of ups is equal to the number of downs. right? In this it is also right. So the number of such paths, how many such paths will be there? I'm not considering just dict paths, any path from here to 2n, from 0 to 2n, how many paths are there? You can tell me your answer in the chat. How many paths from 0 to 2n? In such paths, not dict paths, just such paths. Such paths in which you can go only right, you can go right or up. I'm not considering the constraint that we have to not go below x-axis. That is not considered. Only you have to go right and up. How many paths? Sorry, up and down. This is bad. Up and down. How many such paths can be there? Yes, 2n Correct, correct. Excellent. 2n because out of these 2n paths, 2n ups and downs, we need to choose n paths which are only ups, n moves that are only ups. The remaining n are obviously downs. So this is the total number of ways of choosing paths. Right? Now if I take the last up step, now the number of down steps in this path is called the exceedance of the path. It's a parameter to measure the number of down steps. Okay. So the exceedance of the path is the number of down steps of the path below the x-axis. Below the x-axis, only below the x-axis. So if I take the last path and switch the remaining two paths, a very interesting thing is that the exceedance of the new path is equal to exceedance of the old path minus 1. If you continue doing this, we will understand that all the new paths, there are equal number of paths with exceedance equals 0, 1, 2, 3, and so on. Because the exceedance of number of paths of exceedance n is equal to number of paths of exceedance n minus 1. Okay. So now what we are interested in, so there will be n paths, there will be n total such things. So because there are a maximum of, you can have a maximum of n down steps. Exceedance is the number of down steps below x-axis. Okay, we can have a maximum of n down steps because we can have n down steps and then n up steps directly. That is the most number of down steps that is the maximum exceedance you can have is n. Okay, so that will be the maximum exceedance path. So n paths. So total number of sets will be n plus 1 sets, right? And all of them have equal number of paths, equal number of elements. The dict paths, what would be the exceedance of a dict path? You can answer in the chat and tell me. What would be the exceedance of a dict path? A dict path means it does not go below the x-axis at all. Yeah, excellent. 0. Exceedance of a dict path is 0. So we want all the paths to exceed 0. That would be 1 by n plus 1 of the total number of paths. Because it's only a fraction, all are equal. How do you multiply n plus 1 towards n? There's a Catalan of n. Okay, and the next thing. Catalan is binary trees. So full binary trees, binary tree either 0 or 2. This is a binary tree basically. These are full binary tree. This is also full binary because this one has 2 children, this one has 2 children, these nodes have 0 children. This is not full binary. The number of full binary trees with n leaves. They'll have n minus 1 equal to n nodes, and therefore Catalan of n number of binary trees. So this is a graph indicating the number of internal nodes and the number of binary trees. This is the number of binary trees, the number of nodes. This is basically the Catalan of n only. Okay, all of them. How many ways can I write a positive integer n as sum of three positive integers up to commutativity? Right. So first we'll adjust for positive integers. Each of the parts must be at least 1, right? Because we have only positive integers, not so we first assign one object to each of the parts. This is the objects living up with n minus objects to be freely among k parts, right? So we use stars and bars. So stars and bars is a very classic term for. So we distribute this n minus k identity objects to k distinct boxes. So this part is the sum and n minus k is the numbers. Okay, so According to the stars and bars theorem, the number of ways to reach by triangle objects in y boxes is given by x plus y minus 1, g y minus 1. That's the stars and bars theorem. X is m minus k and y is k. So that is n minus 1, c k minus 1. If we substitute m minus here, n minus k plus k minus 1 is n minus 1, y minus 1 is k minus 1. So n minus 1, c k minus 1. The last thing, and then the session will be closed. You have 6 questions and exactly half an hour left. So you can solve each question one by one. So the first question, I'll give 5 minutes to solve that. I'll solve that in 35. Find the number of ways in which 6 plus and 4 minus signs can be arranged in a line such that no two line signs occur together. Yeah, so all of you can put your attendance in that again. In that, please put your attendance. Who are presenting the call, you can give your attendance. There's nothing no attendance. So One more minute. I'll give you one more minute for your first question. Can you put your answer in the chat? The first one. Okay. So the first one. The question is, find the number of ways in which 6 plus and 4 minus signs can be arranged in a line such that no two minus signs occur together. Because let us see if anyone of you answered this question. Excellent. 7C4. Right. Third question, vowels and alphabet. No, vowels are alphabetically ordered together and consonants are alphabetically ordered together. Third question. Yes. Okay. So the first one, 6 plus and 4 minus signs can be arranged in a line such that no two minus signs occur together. 7C4 is the right answer. So see, 6 plus and 4 minus signs. Huh? 6 plus and 4 minus signs. There'll be 11 places. But if no minus sign has to occur together, that would mean that next to every minus sign, adjacent to every minus sign, there are either two plus signs or at least one plus sign. Because if there is no plus sign, a minus sign will come in, that is not accepted. So to do that, we start in the reverse order. First, we take plus signs and we create gaps between plus signs. 6 plus signs, right? And we create gaps. 1, 2, 3, 4, 5, 6, and 7 gaps. There are 7 gaps. The minus signs now are going to fill in these 7 gaps only. We have 4 minus signs. Okay. So we choose out of these 7 gaps any 4 gaps and fill those 4 minus signs in those gaps. How many ways of doing that are there? 7C, 4 ways. And after putting those 4 minus signs, we just club. So suppose we put 4 minus signs in these gaps. We just remove these gaps and the plus signs will occur together. That's all. So the total answer is 7C4. If there's any doubt, you can ask. Third one is 13 factorial by 5. I do not know the answer for the third one. I will tell you the answer later on. I have forgotten the answers for these questions. So, any doubts you can ask. Can you all hear me? If you can, just put a thumbs up. And can you see me? My screen. Okay, nice. Cool. Nice. So, now the second question. I'll give you 5 minutes for the second question as well. And you can answer the second question. And put your answer in the chat. Second one. 8 sailors on a boat. 3 can work only on one particular side and 2 only on the other side. Find the number of ways in which the sailors can be arranged on the boat. Also note that in the second question, each sailor arrangement is different. We're not considering all sailors, like we are numbering the sailors, sailors 1, sailors 2, sailors 3. You can understand hopefully. that every sailor is distinct, basically. So you have to permute them, not the answer for the first one. I'll just write it down 7C4. Whoever got disconnected or something, this is the answer for the first one. The second one, you can solve and tell me. I will give you 3 minutes more. No, no, no. You have to permute those sailors again. The second one, whoever Patil Raj Sanjay. Second one, you need to permute those sailors. Okay. I will give you 1 more minute to solve that question. And if you can put your answers in the 8C3 into 5C2, 6048. It's not 6048, by the way, but okay. Okay, I'll solve this. So, out of 8 sailors, right? 8 sailors, 3 can work only on one particular side and 2 only on the other side, right? We have 8 sailors. We'll divide the boat into 2 sides, side A and side B. 3 work only on one side and 2 only on the other side. So these 2 sailors and 3 sailors are fixed here. Now we chose 3 sailors, we have 5 remaining, right? Out of the remaining 5, we can choose any 2 people in no, we have 8 2. We have 3 remaining. My bad. We have 3 remaining, right? Out of these 3, we choose any one of these 3 in 3 ways, correct? Any one of those 3 in 3 ways, and put them on this side. Each side will have same number of sailors. No, we are rowing the boat. I hope you understood. That was not mentioned in the question. My bad. Okay, so this question is a little ambiguous. So, but now I think it's clear. So, 4 on each side. So 3 into. We selected those 3 people into, and each side has 4 people. So 4 factorial ways on the first side and 4 factorial ways on the second side. This is your answer. 3 into 24 whole square. That is basically 1728. I think it's clear now. Each side has to have the same number of people for the boat to run smoothly, because you are arranging sailors on each side. They are rowing the boat. Yeah, I had to mention that. My bad. Patil Raj Sanjay. Next question. The answer for this is 1728. How many ways can the letters of the word combinatorics be arranged if all the vowels and consonants are alphabetically ordered? Second question again. All right. Second question again. Second question is, so you have eight sailors on a boat, right? In out of those eight sailors, you're fixing three to one side. So why is this? You have eight sailors on the boat. Out of those eight, you're fixing three to side A and two to side B. Okay. So out of these, we fix three of these to side A and two of these to side B. Remaining, how many do we have? We have three soldiers, three sailors. Each side will have equal number of sailors for the boat to run stably. So out of these three sailors, for this side A, I'm selecting any one soldier. So one sailor. I can select them in three ways. 3C1 ways. So three ways. After I select that one sailor, the other remaining sailor we have, no, remaining two sailors, they will go into side B, obviously, because the boat has to be stable. So after selecting these three, I have to permute the sailors. There will be four on each side now. The number of different ways of arranging, I told you in the beginning itself that all these sailors are distinct. So each different arrangement of sailors is considered as a different arrangement. Each different sequence of sailors is considered as a different arrangement. So 4 factorial into 4 factorial. Because 4 on each side. So 3 into 4 factorial whole square. That is 1728. Yes. 1287 is for what? Consonants and vowels. Okay, I'll tell you. I don't know the answer of that. I did not do that. So Combinatorics, right? Now the vowels O I A O I. O I A O I. We arrange them in alphabetical order. A I I O O. These are vowels in alphabetical order. Okay. The consonants C M B N T R C S. C M B N T R C S. Okay. Now I'll arrange them in alphabetical orders. So first B, then C, M, N, R, S, T. Right? These are consonants arranged in alphabetical order. Consonants in alphabetical order. Now, totally, combinatorics has 13 letters. So I'll leave 13 gaps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13 gaps. Now these 8 consonants are there, no? Here order does not matter because we have only one order, right? We cannot permute them again. We are what it's telling by alphabetical order means is restricting permutation. So out of these 13 places which we have to fit these eight consonants in any of the eight places. So we have to choose eight places out of these 13 places, and these eight consonants will automatically go into those eight places, and we do not have to permute them. The remaining five places will be filled with with these vowels again without permutation because if you permute them, it basically ruins this condition which they have given. So 13C8 or 13C5. If you choose to do it in the vowels, it will be 13C5, which are the same thing because NCR is equal to NCN minus R. So your answer is 13C8. That will be 13 into 12 into 11 into 10 into 9 divided by 5, 4, 3, 2. 3 threes are 6 are 11 into 13 into 9. Right? Yeah. That is 13 into 11 is 13, 13, 143. 36. Oh, this is my bad. 143 into 9 is not that. 36, 38, 12. 1287 is the right answer. Again, nice. Well done, Bottle. 1287. Yep. How many ways can you fully parenthesize an equation with 6 factors? This comes under Catalan numbers. I had highlighted a formula back then. Factors and variables in an equation. You can do a fourth one. Crazy nice. 42. That's the right answer. Why 42? Because there was this equation back then where I had highlighted that The number of ways to parenthesize an expression with n binary operations, or n plus 1 factors, obviously, is given by the nth Catalan number, that is Cn. Binary operations have to come after a particular factor. So 3 plus 2 has one binary operation, two factors, like that. So n plus 1 factors. So here n plus 1 is 6, right? Here n plus 1 here is 6. So n plus 1 is equal to 6, n is equal to 5. So the answer will be Catalan of 5. Catalan of 5 is 1 by n plus 1 into 2n cn. That is 1 by 6 into 10c 5. 1 by 6, 10, 9, 8, 7, 6, 5, 4, 3, 2, 6 and 5. 4, 3 is out. This is twice. Oh, this is 4 times. 80 and 20 is 4 times. 6 and 9, if you divide by 3, you get 2. You get 3 here. You get 2 here. 6 into 7 is 42. Yes. The answer for this is 42. Next, how many Dyke paths of length 6 from 0 to 0 to 6? From 0, comma 0 to 6, comma 0 exist? Again, this is also a basic Catalan number question, which you can solve yourself. Dyke paths from 0, 0, comma 0 to 6, comma 0. Of length 6, yeah. So I'll give you 2 minutes for this. It's basic, very basic. So you can just answer in the chat. No, Dyke paths of length 6. Yes, 5, 5. Correct, correct. Right, excellent, excellent. C of 3. So that's basically 0, comma 0 to 6, comma 0. 0, comma 0 to 6, comma 0. This is 2n. N is 3. So C of 3. That is 1 by 4, 6C3. Because 1 by 3 plus 1, 2 into 3, C3. Basically, that is it. So 1 by 4, 6, 5, 4 by 6 is 5. Next. How many ways can you represent 10 as a sum of 4 positive integers? Great question. I'll give you 2 more minutes for that. 13C3 is not the answer. You are using stars and bars directly. You have to substitute x as n minus k, and then you have to do. You directly use stars and bars for getting 13C3. That's not the answer. Not 93, not 93. No, right, 93, correct. My bad, correct. Excellent. So, n minus 1, ck minus 1. N is 10 minus 1, c4 minus 1. That is 9c3. So, whoever got 9c3, that is the right answer. Excellent. Thank you for participating. And I think I should close with this. Anyone has any doubts, you can ask. I will keep the chat open for 3 more minutes. If you have any doubts in any of these questions, or you want to look at the questions, you can ask. And then I will close the meeting at 11:05. And also, I will be sending a feedback form and a assignment link. So I will give you 3 days for the next assignment, or 2 days. I'll give you 2 days to solve the assignment, which should be good enough time. There are only 15 questions. Takes 2 hours, so 1 hour a day should easily be able to do it. 2 days, and you can submit the assignment. I will send the assignment and the feedback form in the group. Yeah. Thank you. Thank you for attending. Yeah, in 2 days, due date would mean 18th EOD is your final. So on 19th from 19th 12 a.m. in the morning, I'll not be accepting 12 a.m. I'll not be accepting any responses.